So our next speaker is Peter Braam. Peter has founded a new company, Campaign Storage, and we're all familiar with his great efforts with Lustre over the years, and a big contributor in storage systems research, parallel file systems for HPC. So we're definitely very excited to hear about what you're up to, Peter. So yeah, there is, you know, you want to use this one as a carryout? Okay, great.
Good morning. Thank you for having me here, and thank you for all the attention that this conference is giving to campaign storage. So I was asked in this talk to give you a perspective of what campaign storage could be as a product in the market. How does it fit in with other storage technologies? What sort of features should be in there? And how would it be engineered? And so let's take a look at that. I think I'll start with some overview of what is happening in the market space of devices, because there are tremendous changes, and then we will move into the campaign storage applicability to that market. So campaign storage, as you've just heard, was actually invented at Los Alamos National Laboratory. And we visited there a few times, and Nathan Thompson and I founded a company to productize this and add some features. So I'm a great fan of what is called software-defined storage, and so I look forward to partnering with both suppliers of storage equipment, but also end users, depending on how they want to proceed with it. There are several other companies that are working on various aspects of campaign storage. So what you've probably learned this morning already is that campaign storage is a new tier, and there are several new tiers in storage. The burst buffers are one new tier. They are very fast flash or NVMe devices of another kind maybe, and there are probably different burst buffers coming with other kinds of memory. The parallel file system is still in there as a tier. It's an older one. Archives is an older tier, and campaign storage sort of fits between the faster tiers and the archive. Another new tier is the cloud. And so in the new world, there are now a lot of tiers, and what you see is that the bandwidths per tier decrease approximately in order of magnitude. Yeah, so that's quite a challenge to deal with the data transport between something that is 10 times faster or 10 times slower. So if you look at the deployment,
and I'll take that. Sorry to interrupt.
So what Dave has explained to you this morning is roughly the sort of deployment that I'm showing here in this slide. In a research computing environment, you might see some clusters, maybe doing simulations or analytics. And these clusters would typically have a set of compute nodes doing the math and the analysis, and then perhaps a clustered file system like the Hadoop file system or Lustre file system, but also a burst buffer these days with the highest bandwidths. Now, what we'll see in a minute is that storage is very expensive. And the way that people will gradually start to operate with this is by moving data in and out of the faster tiers to something that you could call campaign storage. Yeah, it could perhaps be offered by different storage systems. So campaign storage offers a lot of capacity and data movement. It's a fairly industry neutral tool because it is a file system, and so it can coexist with other tools that you may already have, like policy databases or data management tools, workflow managers, and that sort of thing. We think that this is quite a big challenge. This is a sort of an open architecture for big, long-term storage, and so Los Alamos and we created a steering group for campaign storage, and the purpose really is to find open approaches to data management and make sure that customer needs are heard. And you're welcome to come and attend the first meeting tonight. It's in a hotel not very far from here, and if you don't like the talk about campaign storage, you can always drink or eat something there. Good. So the way that we look at campaign storage is that it is a product line. It is all derived from a core set of features that you could call the campaign storage file system, MARFS. And then there could be slightly different variations, for example, to use it for archiving, for burst buffers, or perhaps in the enterprise. Yeah, and so I think that there would be a couple of varieties of products in this space that each have slightly different opportunities, but they would, for 99%, leverage the same code base. Very important about campaign storage is that it is not an effort to build many things from the ground up. Yeah, it leverages existing object stores and existing parallel file systems for metadata storage. And this makes a huge difference because maturing a bottoms-up storage product is a very long process. And you can see all the gray hair on my head. It was all caused by work like that. Yeah. Good. So let's, for a moment, look at what is happening in the industry. So I think that this is an interesting set of numbers here. So I drew the sort of 1, 2, 3, 4, 5 tiers of memory here. And I put some numbers below that, namely what is the cost for bandwidth and what is the cost for capacity. And the cost for capacity you find in the newspaper every day. Yeah, so there's very little news there. And what you basically see is that the lowest cost is still tape for like a cent per gigabyte. And the highest cost is stuff like RAM for approximately $10 or so per gigabyte. What you see above that is that the cost for bandwidth increases with a same factor 10, but in the opposite direction. Yeah, so to achieve bandwidth with tape, for example, you would need to buy a drive, a tape drive, which is a horribly expensive thing. Yeah, and to achieve bandwidth with memory is ultimately the cheapest. We have 4 orders of magnitude in cost for capacity and in cost for bandwidth there. Yeah, and so this is it's not a small number. It's quite a technical challenge. So that is what we're talking about. Campaign storage targets the movement between 2 of these tiers, perhaps, yeah, or maybe 3 of these tiers. It's not a system that fits every possible application, but it is for managing tiers. By the way, in the enterprise storage, there is a similar problem or case for high cost and low cost. So in enterprises, very often expensive file servers are used. I'm not so sure exactly number-wise how much better they are, but they offer much better reliability and often very good performance. And so this is why people that, for example, run movie studios will buy NetApps or Isilon file servers to have very reliable systems. But these reliable systems are also very expensive, and so they are relatively small, and there is a need to move things in and out of these more expensive storage tiers to a cheaper tier. Yeah. So when you look at tiers, there are many considerations. So there are RAM tiers that are addressable, and they are primarily for computation. And so the idea here is that you would migrate a pointer in some program between one tier and another. For example, you would migrate it onto the chip to HBM, or you would migrate it from HBM maybe to RAM or NVRAM. So another thing that you see with tiers is that starting at flash, tiers are very, very sensitive to the size of I/O. So flash is already 5 times faster on big I/Os than on small I/Os. Yeah, and with disks, that number even becomes bigger. But this really means that there is a need to aggregate small I/Os into big I/Os when you go down the tiers. Yeah, you can't do the same thing at different tiers. Another important difference between very fast tiers and storage tiers is that the very fast tiers have a program internal format. That doesn't really work. You can't really find anything in somebody else's pointer. So that's why namespaces are very helpful. And so these could be file system namespaces or object namespaces with buckets and IDs, yeah, to organize your data. The last one is actually almost like a puzzle. So I think that NVRAM is clearly becoming very, very important. But personally, I haven't been able to think of any good application for NVRAM except as being there for the fastest storage applications. Yeah, it will be much faster than anything else, particularly than Flash even and so on. Yeah, but there is no magic like computing in NVRAM or stuff like that. I don't really know what that would exactly mean or what the benefit of the non-volatility would be. So we mentioned already the role of aggregation, and that really is handled by containers, yeah? So fundamentally, it's unlikely that you're going to see the same behavior in different tiers of storage. You must aggregate, and containers are probably a must-have. So here's a picture of what I imagine will be the important functionality that a container would offer. And so this is a picture that is more or less similar to what you can find on the Docker website. And the application sees containers, you know, maybe with a base layer and then some modifications on it. That could be implemented, for example, with ZFS. Yeah, maybe that's not the right technology, but it's a good example. And so they have things like snapshots and clones that allow you to incrementally modify the file system, but be very informed about what lives at what layer. In order for this to fit into a tier, it's very, very important that these containers can be serialized, that you can send the whole thing as a stream without looking what is inside. Yeah, there could be billions of files inside this thing. That you can't handle in a slower tier. You can handle a stream. You also want differentials, so that if you make a modification to a container, you can stream out the differential. Yeah, and ZFS containers happen to do this very well. A new thing that people want is analytics. So they won't just generate files. They will often generate some small databases with the files. And these are deemed to be very, very important for future analysis. You won't be able to recreate these databases in slower storage. They need to travel with your containers. Yeah? And so this is, I think, what is important for containers. So a big topic in tiers of storage is transparency. And transparency in RAM would basically mean that pointers can migrate between different memories where the compute is happening. Yeah, and this could be memory on the chip, like HBM, or memory just outside of the chip. So this is relatively easy if the pointers are not first-class objects. Yeah, you can promote them and rename them because the programming language will redirect you to the physical pointer. But low-level languages, they will need hardware or operating system support. Yeah, things like page table manipulation and so on. So these things are beginning to appear, and their transparency at the RAM level. For storage namespace, transparency is actually a fairly old thing that people have thought about for a long time. And the idea is that you have some form of location database that tells you, if I'm looking for this or that piece of data, be it a file or an object, where is it? And so you need some kind of location database that is distributed, but also it must offer callbacks to tell you if something starts moving from one place to another. The location database has to tell you, look somewhere else, it has moved. Yeah? But what is beautiful about this, that a single directory that can offer this transparency can be reused for many purposes. Yeah? And distributed log managers did that in the past, and things like Redis and so on are beginning to do that in the cloud frameworks. So from this, you can sort of see what the emerging exascale storage framework is like. In the cluster, you will see applications doing very fine-grained work with containers of data. And there will be a lot of features there that are growly emerging in maybe parallel file systems, but particularly in the new I/O libraries like Deos and HDA5. Things like transactions and often peer-to-peer communications for fast synchronization, some erasure codes. And what you see here is that multiple forms of data will be managed in the containers. Some data might be completely local, other data will be consistent in the cluster, but some data doesn't have to be 100% consistent in the cluster, it merely needs to be findable. Yeah? So if it might be handled by one node, but if that node dies, you will need to find its snapshot back, perhaps, yeah, or its checkpoint. So the migration to slower tiers will happen with mover software, yeah, and the mover software will take this to a long-term repository of some kind. That long-term repository has very different qualities, yeah. You need low cost for the capacity, probably hundreds of gigabytes per second of bandwidth, but not terabytes, and the capacity will be very large. The integrity is very important. Yeah, this data is going to stay here for a long time. It needs to be protected from bit rot and things. It also needs to be manageable because enormous volumes of data end up in these longer term archives. Yeah, and I think the faster parts, things like burst buffers and so on, they are going to be almost of a transient nature. A job will start, it will use it very intensively, and then the results from that job will migrate back out to make place for the next job. Just one or two comments about object storage. So object stores are, a very important development that has had an enormous time of evolution, but has really come to mature in the cloud. So they have massive scalability, excellent storage management. There's a simple API, you put and get objects, that's more or less what it's all about. And it runs on very cheap hardware. So it has been very, very successful, but it does have a few cons. It lacks data organization. Yeah, there is no namespace, and these buckets tend to get very large. And I know that people find that difficult. They need databases or namespaces to organize the data. The APIs don't allow for any concurrent access, not from one application, not from multiple nodes, yeah, and this is a problem for distributed applications if they can't work in a sort of process per file, file per process model. Performance can be disappointing, and it actually turned out that they are very difficult to reuse as a component for a storage system, and this is what Los Alamos kind of achieved with MRFS, is to say, we are going to go for it, yeah, and we are going to use object stores. We'll deal with the compromises as they gradually emerge. The attractive alternative seems to be still an open problem, namely build an object store that has normal read-write commands, more or less, yeah, similar to POSIX. It can maybe do non-overlapping distributed I/O, has three-tier hierarchical redundancy in a box, in a rack, and in a data center, and it has a coarse transaction protocol. Yeah, pull a snapshot across all your I/O. If you have that, I think things would become a lot easier to integrate with other storage systems, and different applications could use these object stores. Okay, so let's have a look at campaign storage. I already showed you this picture where it sits. So let's see what it is. Yeah, so it's a file system, but it's not a general purpose file system. Now, there are no general purpose file systems, yeah? Some file systems are maybe very good for performance, other file systems are very good for reliability, but there are always fairly big compromises, yeah? And campaign storage file system, MRFS, has its own compromises, but it's good for migrations, yeah? Staging and archiving, meaning bringing the data into a faster tier or getting it out of a faster tier, that's what it's built from. I mentioned before, it's built from existing storage components. Yeah, so there is no aim to re-implement object stores or file systems. Low-cost hardware, very scalable. Roughly, the bandwidth is 10 times lower than a burst buffer or a parallel file system. Yeah, maybe 10 to 100. But it's also maybe 10 to 100 times faster than a tape archive. Yeah, it sits sort of in the middle, and that's exactly what the target is. So if we look at the implementation, there is on the left side here the core storage system. So this is the operating system with a file system and it's implemented with Fuse, and then MarFS is the particular driver that glues the objects and the namespace together. It's a very simple driver, but it does important things. We'll see a little bit more about it, but probably Dave has already told you more than I will. Then there is a management component. What can you do with data in campaign storage? So analytics and search are important. Yeah, how do you divvy up this data? Where is it stored? Who owns it? What kind of files are it? You need things like migration and containers, and these are a few of these things my company is working on, and a few of these things are actually opportunities, I think, for many companies to look at. Then there are data movers. So there's a very beautiful data mover that Dave probably told you about called PF Tool. It's an MPI data mover that's very fast. It looks like rsync, but then clustered. So you can run rsync in parallel on maybe like 10 or 100 nodes and achieve a lot of scalability with it. But other problems need slightly different movers. For example, hierarchical storage management usually does a bunch of extra things. Yeah, it preserves the namespace, it sets extended attributes and so on. So there might be movers needed for HSM, and we actually built one. Yeah, and there would be 2 families probably for Lustre and the other systems with the MAPI. Enterprise NAS would have a different mover again that would probably be very compliant with both things like Active Directory, but also the CIFS or SMB protocols or NFS. And many people have asked for Grid FTP already, which is sort of a standard parallel data mover that probably can be fit relatively easy onto campaign storage. So let me skip this picture, but remember there were clusters and campaign storage, data moving back and forth. And let's see how these components could actually be deployed. Yeah? And so the picture on the right summary expands when you get when you look at what is running on a cluster. So let's start in the middle. And so there might be 3 different kinds of object repositories. Yeah, there might be a disk object store is maybe possibly the most likely one. This could be a commercial one or an open source one. MarFS already supports quite a few, and they're very easy to add. There could be archival ones. So we have had some luck with the Black Pearl object-based tape system that SpectraLogic builds. It is just an object store, but I'll tell you in a little bit later that there are actually some special points about handling tapes that require a little bit of work to use it well. Some of these objects would really benefit from POSIX semantics. So perhaps people want to store sparse file in campaign storage. Yeah, sparse files are not supported by most object stores, maybe actually by none almost. And so those objects are perhaps best stored right in the campaign storage file system where POSIX is available. Yeah, it's not as scalable as using the object stores, but you have more features. So the metadata repository, it's in fact very flexible. All you need is a POSIX file system with extended attributes. Yeah, and many have been tried. Livermore is running, Los Alamos is running with GPFS. We have focused on Lustre over ZFS for a variety of reasons. And the beauty of it is that nothing special is used about the file systems. But different file systems maybe come with different utilities for data management. Yeah, and so there's an opportunity there to explore what works best and maybe make enhancements. So to move and manage stuff, you need mover nodes. Yeah, and the minimum number of mover nodes is 1. Yeah, and now how do these mover nodes actually get access to the data in the faster tier? And in the slower tier, in the campaign storage tier, they will typically just mount file systems from both tiers. Yeah, that's the simplest way to make connections. The mover software runs on these mover nodes. So it might be a cluster of mover nodes and a distributed application. It might be a single mover node that is driven by a single program. So the management will also run on mover nodes. So things like managing the search and analytics, which I will tell you a little more about in a few minutes, third-party data movement, for example, to migrate data between different object stores, will be initiated from the mover nodes. So the mover nodes are really your interface with the campaign storage system. When we go one level down, we can see that the data layout of MARFS. And the data layout of MARFS is actually very, very simple. So on the left side of the dotted line, you see what is called the metadata repository. And the metadata repository is just the folder structure from this underlying file system that I've mentioned a few times. So you put your names and inodes in there, perhaps completely as normal, as you would normally do. But you use the extended attributes to indicate where the data resides. And so these extended attributes, they might point to a single object, which would then reside on one of the object stores. But there are a few other interesting things you can do in campaign storage. For example, you can pack multiple small objects into one big object. And this is actually quite important because the latency of these object stores is very, very high compared to the latency you would get for small file systems, small files in a fast file system or a burst buffer. So this one form of containerizing data is to pack them in an object. There are also very, very large objects in use now, petabytes in size, and these don't fit on one object store. They must be striped over multiple object stores. So a different layout would be to stripe them. And in that case, a little extend lookup table is needed, like what belongs where in the striping layout. Not so complicated, and also exactly what you would expect. If you were to sit down over a cup of coffee with a friend, you would draw this diagram, perhaps in exactly the same way. There is nothing magic about it. So let's look a little bit at search and policy management. So when I started this company, Campaign Storage, for the first sort of 6 to 9 months, I went around and talked to a lot of people to find out what are the archive technologies doing for you, and what are they doing well, and what are the sort of stumbling blocks. We did some testing in a lab, and we kind of found out that one of the big issues is what is called a database, a policy database. So often archival systems crawl your file systems and build a rich index in which you can perform searches and so on. What we found is that those crawls are very slow. The resulting searches are also quite slow. And for a very long time, I had already thought about a different kind of search system where you basically give every directory information what sits in its subtree. So for example, if you have a home directory of a user, you may wonder how many files are there in this home directory, and that could be a lot of files. And at the moment, the only way to find out is to run something like find on that home directory and add up how many files or how many bytes are there. What if you summarize that with a small database, and you capture, for example, how many bytes, how many files have this or that property, and that property could be it's a video file, or it could be it's a property of geospatial location. How many files relate to this or that location on the planet? What file servers are used in this subtree? And so there are quite a lot of these histograms that are useful, and the histograms actually turned out to be the pivot of what people do their data management with. They often have this very big database sitting out there, and the first thing they're going to do is build histograms to get a feeling, what do I need to do to organize my data? How much old data is there? How much big data is there? And then they begin to apply some policy to move it somewhere else or remove it or something like that. It's, by the way, not at all a new idea. This idea has been around for, I think, maybe dozens of years. It may actually also relate to so-called multidimensional database tables. It computes more or less what the aggregates are. The beauty is you can add it very easily to CFS, and the reason is that CFS has these snapshots that I already showed you, and they have beautiful change logs between them, and it helps building completely consistent databases with histograms to do some analytics. So the key properties of this system are that you generate it initially from a scan. Yeah, so you want to start early on so that you don't have so much to scan. Then you update it with change logs. Yeah, so you have to be careful. You have to design your histogram in such a way that you can apply the change log to it and update it. Yeah, if you put information in it that is too general, you will not be able to do that. Yeah, but there are a lot of cases for which you can do that very easily. You want to keep the database 100% consistent with the snapshots. I believe that this is very important because the normal policy databases are live objects. They keep tracking the file system. They're never completely in sync with it. And I think that limits their usefulness because when you actually apply a policy, you will often need to do a comprehensive operation that is 100% correct. For example, back up all the files from a particular user or with a particular property. And these live databases that follow changes in a file system are very difficult to use for that. Now, another very important thing is these histograms have a beautiful property of additivity. So if you put in a subtree, you can keep all your histograms and you just tell the parent, well, there's a new subtree, so increase all your numbers a little bit by what is in the subtree. Yeah, and so just with a few additions, you graphed a whole subtree with a lot of information into the histogram tree. And this allows for the motion of containers with analytics and integration of these containers into the file system. So here's a simple example. Yeah, so the root histogram might tell you how many terabytes and files you have and maybe some other properties. Yeah, so how many are on this or that particular file server, how many have never been opened. And then some user directory is actually a subset of what you see at the top. Yeah, it adds into it because the idea is you see everything in the subtree. If you build a multi-dimensional histogram, things like file type, file size, and maybe access time, then you get limited relational algebra on your searches. Yeah, so you can then combine how many files of this type and that size and this access property are there. Yeah. Without multi-dimensional tables, you will have limited search expressions. Yeah, but you can customize the histograms very easily, so you can get them to be right for your data management also, if you prefer that. Okay, just a few other things. Data movers. So the data movers that we have today are the LANL parallel rsync tool, PF tool. There's a Lustre HSM mover. This is a moderately involved thing I'll tell you about in a minute. And the beauty of the movers is that they can pack and stripe files. Yeah, so you can put small files together and big files on multiple object stores. So what I think will be coming is a DMAPI version of the HSM mover so that it can work with the other cluster file systems like Quantum and IBM's file systems. Grid FTP, as I mentioned. But the most important thing that would help and enable data movers is to increase the POSIX compliance of MARFS a little bit. At the moment, these data movers basically have to follow the sequential write to a single object model that the object stores offer. And if we make some changes on this object layout and allow overwriting of objects, for example, or writing them out of order, then many data movement utilities will just work out of the box. This may sound like a challenging project, but it's actually also fairly old. And for example, the entire Dropbox system is built in this way. Dropbox breaks up its large files into many objects, and each of these objects is of moderate size, like 4 megabytes, I think, or so. And so they allow overwriting and basically POSIX semantics on objects by breaking them up. And MARFS could do the same thing really quite easily. So on the front of metadata movement, today MARFS offers a standard metadata API across multiple file system namespaces. So its performance can scale very well provided you use the breadth of the tree. Yeah, if you go only very narrow and deep in the tree, you will basically be using a single file system at the moment. What is coming here is bulk integration and striping of metadata. Los Alamos has a couple of projects. I showed you what you can do with containers. Yeah, you can graft containers in a namespace, and that will allow much faster movement than you can get with individual operations. The accompanying analytics are also very important parts of moving the metadata. So here's a picture of the parallel file tool. I don't know if Dave already showed you this picture, but it's has a beautiful task queue model where some operations run over directory content, others run over attributes, and then there's data movement tasks. And so it's almost like a distributed job scheduler that makes work items available and then has workers attacking this and reporting the completion. Yeah, again, it's easy to draw this picture, but it's perhaps quite difficult to write a program that's correct and does it efficiently. Yeah? By the way, one of the most beautiful features of PF tool is that it will restart very efficiently. That's one of the few frustrations with rsync, is that if you if you kill an rsync loop, it does have to scan the file system again. And PF has some clever tricks, PF tool, to pick up where it left off. It's much, much more usable because of that. The HSM mover that we build uses an object protocol that is very closely related to S3, but it has features for so-called bulk handling. So when you deal with tapes, it's very, very important that you don't keep moving the tape around. And so, for example, when you want multiple files out of an HSM, you would tell the tape, give me these 100 files back, and the tape device would organize for you in which order it will deliver the files. Now, this looked like quite a puzzle to me initially. I thought, boy, I've never seen that before. And then I realized that that's actually not really true. So this is really doing scatter, gather, I/O, but not for multiple extents in one file. It's scatter, gather, I/O across multiple files. Yeah, so you're basically saying, I need 100 files to move from here to there. You determine the order. Yeah, I only tell you what is the source and the destination. And so we built a rather nice little library that supports scatter, gather, I/O for a number of files. And it does very nice things. For example, it can pack small files into a big file. Yeah, because that tells you, I have maybe 100 small files, put them at this and this and this place in one destination file. So that's packing. Yeah, and the other important application is that the system can reorder this. So it's a good example of some of the new features that can be explored in this space. Yeah, there's borders on what you perhaps would call, research. Could be a new system call. Yeah, and many system calls were added for vector I/O factorization, but this one is not there at the moment. Yeah, and so this, I think, it's a good question. Do we need this one? It certainly looks like it's handy. So let's wrap up the talk with looking at a few of the use cases. So the high-performance computing, or research computing as people begin to call it, the important things that campaign storage can offer here is, first of all, what I would call support for the ecosystem. Yeah, so I think the fact that campaign storage is a file system is very important, because it's not a proprietary interface with that, and many other utilities can leverage this. When you go to more basic use levels, you can say, okay, it can stage and destage, yeah, which Los Alamos is showing is working quite well. HSM, and HSM is quite a rich topic about which we could talk for a long time, but for example, The model here is a little bit different than it might be with tape, because we would maybe want to build a metadata image of the file system first in these namespaces of campaign storage, build the analytics for the subtrees, and then start the policy manager. That's a little bit the opposite way around of what happened in traditional HSM systems, where these policy databases are built in the source file system, yeah, and not in the archival side of the storage. Campaign storage will probably want to support hot and colder locations, yeah, data that frequently needs to move back and forth between the burst buffers and the campaign storage will need to be made available in faster object stores. Many people have asked me about multi-site, and the answer is very simple, because most object stores support remote replication. ZFS supports remote replication using the same mechanisms as underlying the snapshots, and so this is an ideal system to build a remote replica of, particularly for disaster recovery. If you don't have to use it actively in two places, it's easy to build. Another interesting structure in object storage and in CFS are the containers, like buckets for objects and namespaces for the file system. And I think that this is a great opportunity to bring organization to data. For example, why not store a user's home directory or a particular project in a bucket with its own namespace? Because these buckets and namespaces are supported by very good data migration tools. And so, for example, you could extract a project to the cloud relatively easily with this by simply taking a small piece of this big CFS file system and say, well, that's actually what belongs with this project, yeah? Let's put that in the cloud together with a bucket of objects. Amazon has made it quite cheap to move buckets of objects into the cloud, because they will ship you a little appliance called a Snowball, and you can copy locally onto it with very high bandwidth and use UPS or FedEx to ship it back to their warehouse. Yeah, so the wide area networking, which is a real bottleneck for large volumes, is snowballed away by Amazon. So in the data center, you will see slightly different requirements for campaign storage. In that case, maybe there would be an offload of things like NAS file services from fast servers to campaign storage. Yeah, so you would want to export a NAS protocol from campaign storage. Again, the single project extraction is valid there. Also, perhaps to build a global namespace for all the file shares that are available. Yeah. Hot and cold locations we already talked about. Good. So I think that the future of this is to challenge the established, somewhat proprietary nature of data management. Yeah, I think what we would like to propose is, let's sort of go back to things like file system APIs and see how far we can get with those. And clearly there is quite a bit missing in this space. For example, the file system people nor the data management community has ever agreed on a single view of where is data located. Yeah, what does a layout API or structure really look like? Similarly, many attributes are used by different data management tools, and there is no agreement on what these attributes really should be between one storage product and another storage product. So you get sort of a vendor lock-in at the data management level in areas like layouts and attributes. Similarly, everybody is building their own interfaces for workflows. Workflows are very often bulk operations on file systems, meaning moving lots of objects, moving lots of names, and the Unix APIs, which have been tremendously successful, unfortunately only work one object at a time. Yeah, one file at a time, one directory at a time. There are no calls to move whole subtrees, for example, in file systems. Yet, if you think about it, many storage applications, like Dropbox, for example, rely precisely on that. Yeah, how do I migrate all the changes that are made on a computer, in this case to the cloud? So I think this is a great opportunity, and I'm particularly hopeful that the the working group that we've created can maybe have good discussions. So the conclusions are, there's a lot of new hardware out there, and as a result, people have started to build new software, yeah? And campaign storage is one of these things. The other thing we saw is constructions of containers and the very fast I/O libraries that are needed. I think that the bulk aspect of data movement is perhaps one of the most interesting questions. Doing that for both data and for metadata, yeah, deal with lots of files and lots of data at the same time is a great challenge. I think I'm going to stop here. We have time for a few questions, I think.
Okay. Thank you, Peter. Are there questions for Peter? He's pretty shy here. Okay.
So I'll ask the same question that I asked David. I've never heard of any other future-looking storage architects talk about the need for more POSIX and more file systems looking forward. Do you really expect file systems to be the path to the future, or is it just a stopgap?
I think this is a very good question because we don't really know the answer. So historically, and this is probably what Dave answered, is when more and more objects started to arise, people needed organization, yeah? And a file system tree is one form of organization. You could also store it in a database, yeah? It doesn't make a very essential difference in this case. What I've heard is that objects without a namespace are difficult to manage in organizations. Whether some replacement of file systems will come into play, I don't know. But I do want to point out that there is a challenge with a different organization, namely a different organization of the data will likely be proprietary. Yeah, and the big success of reusable applications has been possible only by having a reusable interface. And you know, we begin to forget that things like you know, Google Drives and Dropboxes and all these kind of things, they're actually totally locked up. Yeah, you have. It's very difficult to run your storage applications on a Google Drive. Yeah, there is no rsync for Google Drives or Dropbox, I think. Yeah, that would have to be completely reconstructed for the new APIs. I think it's very costly. Yeah, I think there may very well still be a very good opportunity for data management to leverage standard APIs. But you know, you never know what will happen in the future.
Okay, other questions? Okay, guess we're all shy. Okay, again, thank you very much, Peter.